Alright, so you would have done the velocity and ticket timer prac. This is to use the dynamics trolley to roll it along with the ticker tape and to measure the instantaneous and average velocity of that trolley. Part of the dot point requirements is to get quantitative data, so numerical data, to look at what instantaneous and average velocity, how they are different to each other, and then to look at the graphical representations and interpret graphs. So that's going to be our talking point here. The idea or the syllabus outcome we're covering here is this one highlighted in purple. So conduct a practical investigation to gather data to facilitate the analysis of instantaneous and average velocity. As we said again, we do come across a little bit of this as well, because it says conduct practical investigation, select from a range of technologies to record and analyze motion in various situations in one dimension. So we are only dragging it from one end to another, so that is our one-dimensional end. And we do use that to help us calculate time, displacement, velocity as well. Okay, so let's have a look at the actual aim of this investigation. It's to use dynamics trolleys to find the instantaneous and the average velocity using ticker timers. Okay, when we found the data, we're going to plot it as a displacement time graph, and we're going to look at how differently average velocity and instantaneous velocity can be found. Alright, so let's have a look at this. On a displacement time graph, if you're trying to find the average velocity, it's the total displacement divided by total time. How do we know this? Or how do we do that on a graph? It's just using the gradient. So we know that the gradient, is just rise over run. That we already know. Okay. On a displacement time graph, we talked that the rise is our displacement. Our run is the time. If you have a look at what we have here, time is down here, and displacement or change in position is over here. Okay? If you go from the very starting position of your data or your trend line to the very end point there, and you draw a line of best fit, so this dotted line we have here along here. Okay? That will be the average velocity we have. On the right hand side, we have a scenario of trying to find instantaneous velocity. So at this particular point here, we are trying to find the instantaneous velocity of the object at around about 3.5 seconds. So we're trying to calculate how fast is that object moving at 3.5 seconds. To do this, again, you're going to draw a line of best fit, or you're going to draw a line of best fit along here, or a straight line tangent, and we go along there. Now, the key thing to note is when you're drawing the tangent line, that line, the straight line you draw, it only touches the curve of that specific time. Okay, so you're only going to connect that tangent line to this point here, the designated time that we want, and we draw it out like that. Once you've done with that, you're going to then try and find the rise, and you're also going to try and find the run of this chart here. Again, rise over run will give you velocity over displacement time, and so that's how you find instantaneous velocity in this prac. Okay, just a few notes on what we're doing for this. So we have our dynamics trolley. This here. We have ticker tape, we have a ticker timer, and we have carbon paper. Now, when you do this prac, the carbon paper has to be on top of the ticker tape, because that's how you create the little dots. Okay? So on the ticker tape, you'll see sort of little dots form as you go past it, like this. Okay? This is an example of constant velocity because the spacings are relatively similar to each other. In terms of counting for time, okay, each dot, if you're using AC current and the power supply, a 12 volt or any volt battery will generate 50 hertz of vibration. So that's the frequency, or how frequent does it tap once and then to the next interval. We know from waves that the frequency is inversely proportional to the period, which is how many vibrations we get. So if we flip that equation around, it becomes 1 over 50, and so it means that every 0.02 seconds, that's how long it takes from one tap to another. Okay? And we can use that to our advantage. So if I line it up to where I see the very first clear dot on my ticker tape, and I count 1, 2, 3, 4, 5 gaps in between, or you could say 6 dots. Okay, this entire length here is approximately 0.1 seconds in length. Okay, so now that I know the exact time, I can then calculate the distance or the displacement traveled by this trolley, and then I can use that to find its distance traveled in intervals of that particular time, so I can keep it consistent with it. Okay. When you use your ticker tape, as I talked about earlier, you will find that at the start the dots will kind of clump together. You only start counting when you see a very clear dotted line showing in front of you. So that's kind of the idea you're trying to achieve here. If you were to accelerate the trolley, obviously you'd find that the dots will start close to each other, and then they get progressively further and further away. Okay, so that's kind of what we talked about here. We're trying to count 5 different spaces instead of 5 dots. Okay, so 5 spaces or 6 dots would be the way to go. Alright, so if we look at the actual data you should have the accumulated time. So taking it to round about 0.7 seconds, you could go a bit shorter or a bit longer. So long as you have 5 data points, that would be the best possible. You have distance per interval, so how far has it traveled per interval of 0.1 seconds. Obviously measure that with a ruler. Obviously the distance traveled isn't going to be very far, so some of you might have written it in centimeters and millimeters. That's fair enough, but the SI units for velocity at the end is meters per second. So you should convert your distance back into meters per second as well. Okay, so all these numbers will be measured in meters. Okay, so this is the scenario of constant speed. How do I know it's constant speed? Because the same amount of time has passed, so each passing interval is 0.1 seconds, but you can see that the car or the trolley has gone 0.05 meters consistently in each time interval. Okay, so if there is no difference in the time intervals of that object, then you know you've made constant progress. Okay, so this is an example of constant speed. Each interval of time, the same interval of time, you will travel the same amount of distance. we also have here the accumulated distance. This is what we're going to be using to graph out the data. Okay, so this is what we have. Now, just to remind you, when graphing, title, labeled axes, and then ensuring that when you're graphing, the units are increasing in incremental proportions. What do I mean by that? If you were using graph paper to graph this, to go from 0 to 0.1, you use 5 boxes to help you do that. Then make sure the next time you increase it by 0.1, you've also gone past 5 boxes only. If it goes 6, then obviously it's not incremental. Alright, so there's that. Now let's actually analyze this graph here. So when you plot the graph, you have the dots, and then you should be able to see a trend line. Now if it's a straight line, or if they all kind of line up together like this, you can just draw a line of best fit that is straight, that goes through the dots. It's not very well done by me here, but you get the idea. Okay. And then the next thing is to do, is work out the velocity. Now, like I said before, the gradient is our rise over run, which in this case is displacement over time. That formula leads us to velocity. So the gradient on a displacement time graph is the velocity of the object. The gradient that I have here is 0.5, which means that the velocity of the trolley I was moving at 0.5 meters per second. How do I determine the units? Look back at how you labeled your axes. So on my y-axis I labeled it as meters, and on my x-axis I labeled time as seconds. So that's how we work from there. The next example we have is acceleration. Now you can tell that this object is accelerating because the distance intervals are increasing. So for the same amount of time that's passed, I am going fast or further than before. Okay, so I'm traveling further and further away. The accumulated times or accumulated distance is also given to you there. So let's have a look at how we find instantaneous velocity from that. Okay, so here we have our graph. As you can see on a displacement time graph, if the trend is curving upwards, then it's an accelerating object. Yeah. If I want to find the average velocity, it'd be from one point of my graph to the other point, and you would draw a line of best fit, sort of like that. Well, straighter than that. I am using a mouse to help me freehand here, so it's not as pretty. But this would be your average velocity there. Okay? Now, the question is, how would I find the instantaneous velocity? Actually, before I go on to that, I want to note down drawing line of best fit. What does that actually mean? A line of best fit can be straight or it can be curved, but the idea is the trend line is going through the dots. If you actually look at this dot here, that dot there, and that dot there, none of the line doesn't actually connect the dots. It actually goes in between the dots. So that's trying to show the average of those data sets. Okay, next thing we can do is find instantaneous velocity. So I'm going to use 0.2 as my example. Remember, if you want to find instantaneous velocity, you draw a tangent to the curve you are trying to measure, and then you extend that line out. Okay, so I have it here, and then along here. Okay, so this will be the point I designate as instantaneous at 0.2 seconds. So started at about, measured at 0.15, it's about 0.3 or a little bit less than that, but just for simplicity's sake, that's 0. And if we go there, so that's roughly 0.2. So at 0.2 seconds, if I use the gradient formula, it will be y2 minus y1, so our y2 is 0.2, and our time is 0.3 minus 0.15. So plug that into your calculator. And I get a value of 1.3 repeater. That means at t equals 0.2 seconds, velocity was 0.13 repeater meters per second. And you can do the exact same thing for 0.6, you can calculate that, find the instantaneous velocity of that, and you would see that because it's accelerating, the velocity here at 0.6 will be bigger than the velocity we had at 0.2. Okay, so that's how you graph it out. That's how you depict instantaneous velocity. Maybe I'll just label that. So we have instantaneous velocity here. That's how you calculate it. Draw the tangent line, and then you have average velocity, which is drawing the line of, or a straight line from the start to the end point of your data set. So that's how you do it graphically, and also we've shown how they're different in terms of the data we set using the set time intervals. Alright, if there's any other questions, please let me know. But that's the end of this explanation video of how to analyze the instantaneous and average velocities using tick timers and trolleys.